Welcome back to the deep dive. Today, we are strapping ourselves into the theoretical cockpit for a truly ambitious journey to the very edge of fundamental
I think
physics.
that's the right way to put it.
For decades, the two magnificent pillars of modern physics, general relativity, which describes gravity as the geometry of space-time, and quantum mechanics, which governs the subatomic world, they've operated almost entirely independently.
Right. They speak different mathematical languages. They apply to completely different scales. And, trying to unify them is still the biggest challenge in
The
physics.
holy grail, yeah.
And this deep dive, it focuses on a crucial moment in that quest. It's one of the most, I think, elegant and concrete attempts to bridge that gap on a really fundamental level.
Okay.
We're looking at a system that is quantum mechanical to its very core, the simplest possible atom, the one-electron atom. And we're asking a pretty bold question.
Which is?
What happens when we place it directly into a spacetime that is locally curved by gravity? Can the warping of space itself actually change the fundamental properties of matter?
Okay, let's unpack this, because we're not talking about, weak general gravitational effects that just bend light or pull a whole atom.
No, not at all.
We're talking about the fabric of spacetime itself exerting a differential force, a tidal force on the atom's components, and fundamentally shifting the electron's orbit and its energy levels.
That's it. Our source material today is a seminal 1980 paper by Leonard Parker, published in Physical Review Letters, titled One Electron Atom in Curved Spacetime.
A true classic.
Absolutely. Parker was a pioneer in quantum field theory in curved spacetime, and he set a very specific, very rigorous goal here. The task was technical, but completely necessary.
He wanted to find explicit mathematical expressions for the shifts in the energy levels of this atom.
Exactly. Specifically, the key low-lying states, things like the 1s12, 2s12, and 2p12 levels. And most crucially, these shifts had to be calculated to the first order in the Riemann tensor.
The Riemann tensor, that formidable mathematical object that encodes every last detail of local space-time geometry, tidal forces, how geodesics diverge, all of it.
All of it.
So if we strip away all the tensor calculus and the complex math for a second, what's the ultimate mission here for you, the listener? What are we trying to find?
The mission is, I think, simple, but also really profound. We want to know if the light emitted by an atom, its specific spectral signature, the precise color and frequency, can act as a fundamental probe of the local geometry of spacetime around it.
So can we find a surprising, unambiguous signature of that curvature, but embedded directly inside an atom's spectrum?
That's the question. And Parker's work provided the definitive theoretical proof that, yes, such a signature must exist.
Right.
And it offered a potential path for future measurement in regions of extreme gravity where that space-time warping is significant.
All right, let's jump right into the core insight then, because this is what elevates the paper beyond just a theoretical exercise. If I put a hydrogen atom near a massive star, its energy levels are going to shift. We know that.
We do.
But why is the specific shift Parker calculated, the one caused by local curvature? Why is that so unique and important compared to effects we already understand, like the standard gravitational redshift?
This is the critical conceptual differentiation.
Yeah.
And it's what makes this effect so challenging to measure, but also so powerful theoretically. Think about the usual gravitational redshift.
Okay.
It's a consequence of the overall gravitational potential difference between the light source, so the atom, and the observer, us.
Mm-hmm.
So when we talk about standard redshifts or even the familiar Doppler shifts from motion, those effects are uniform.
Uniform how?
Well, if you have an atom far away in a strong gravitational field, the light it emits will be redshifted. That means all of its spectral lines, every single one, the lines for every electron transition, they all move by the same proportional amount.
You used the analogy of a musical score being transposed before. I like that. The entire spectrum shifts to a lower frequency, but the relationships between the individual notes, the gaps between the lines, they stay identical.
Exactly. The ratio of the frequencies remains completely unchanged. The curvature shift, however, is fundamentally different. It's different because it interacts with the internal structure of the atom.
Ah.
The curvature of spacetime acts like an external geometric field that is non-uniform across the tiny extent of the atom. And Parker's results show that this local curvature perturbs each energy level, 2s, 2p's, 2bellers, 2dollars, 2nulls, and so on, to a different extent.
Oh, so the pattern itself warps. If the $1 level gets pushed down by, say, X amount, the $2 level might be pushed down by Y amount, and X is not equal to Y.
Precisely. Because those energy gaps between the levels change differentially, the frequencies of the photons that are emitted change disproportionately. The transition from 2p to the $dollar might shift by one amount, but the $2 transition shifts by a totally different amount.
So it changes the natural ratios between the spectral lines.
It does. And that differential perturbation is the key. The spectrum doesn't just transpose. Its internal shape changes entirely. It's like the musical score isn't just transposed, but the intervals between C and E and between G and B have been subtly stretched or compressed.
And that unique internal change in the shape of the spectrum provides what Parker called unambiguous information about the local curvature.
That's the phrase. It is the distinct geometric fingerprint, and it's embedded directly within the atom's internal physics, independent of how fast the atom is moving or how far away it is in the gravitational potential.
That is a critical theoretical distinction. I remember that Parker noted there were contradictory conclusions in the literature before his work. Why was this so controversial? Why was it so hard to figure out if this internal differential shift was even theoretically possible?
Well, the difficulty really came from just combining the formalisms. General relativity is generally deterministic and smooth, while quantum mechanics is probabilistic and highly dependent on boundary conditions.
Two different worlds.
Completely. And earlier attempts often used approximations, like treating the electron classically or using the non-relativistic Schrödinger equation. Some just confined the study to really specific, highly symmetric spacetimes, like idealized cosmological models.
Which isn't the real universe.
Right. Parker's approach was different. He used the full, generally covariant Dirac equation. This ensures that special relativity and electron spin are handled correctly. And then he applied it using a generalized perturbation theory based on the Riemann tensor.
And that's what showed definitively that curvature acts like a true external geometric field interacting with the quantum system's internal degrees of freedom.
Yes. Before Parker, it just wasn't universally accepted that the geometry of space-time could cause a differential splitting of energy levels, distinct from just a uniform gravitational potential effect.
Okay, let's get practical now. If this effect is so profound conceptually, how large is it? If we took a hydrogen atom and put it somewhere with a measurable but weak curvature, would we ever see this? I mean, our spectroscopes are incredibly precise.
This brings us directly to the scale calculation that Parker included, which immediately shows the challenge. He quantified the size of the effect by comparing it to the Lamb shift.
Okay, for anyone not familiar, the Lamb shift is a tiny quantum electrodynamic correction that splits the 2s12 and 2p12 levels in hydrogen.
Right. A really subtle effect discovered after World War II, showing the power of quantum fields. Its magnitude is tiny, about $4.04 times 10⁷ electron volts.
So we're defining appreciable as being comparable to the Lamb shift, something that's very hard to measure, but we definitely know exists. What kind of curvature do we need to generate a shift that big?
To generate a shift of that magnitude in a hydrogen atom, the characteristic length or radius of curvature, which Parker labels dollars, would have to be, well, extraordinarily small. The calculation concludes the dollars would need to be only about 199 centimeters.
199 centimeters. That is 10,000 kilometers. Let's just stop and think about that.
Mm-hmm.
That means to generate a curvature-induced shift equal to the tiny Lamb shift in a hydrogen atom, you'd need to place it in a space-time where the local curvature radius is only 10,000 kilometers. That's roughly the diameter of the Earth.
Correct. Now compare that to the real world. Near the surface of Earth, the characteristic radius of curvature is roughly 10 centimeters, far, far larger than 199 years.
Not even in the same ballpark.
No. Even near the sun, it's still dramatically larger.
So if the effect is so minuscule, I mean, vanishingly small in weak gravitational fields like ours, is this research purely a mathematical curiosity? Is it just proof that we're decades, if not centuries, away from ever observing this?
That's a fair challenge, and is why theoretical physics often advances faster than experiment. But no, I don't think it's just a curiosity. First, the result provides a critical upper limit. If we can measure the Lamb shift with high precision, we are simultaneously placing a very stringent upper limit on the maximum local curvature we're experiencing. If our measurements of the Lamb shift didn't match theory, one of the first things we'd have to check is if we're missing some kind of background curvature effect.
I see. It's a constraint.
It's a constraint. And second, and this is more important, the principle remains absolutely vital for astrophysics. While the effect is tiny here, the theoretical framework gives us the language to analyze extreme environments.
You mean like near neutron stars or black holes?
Exactly. The possibility of placing upper limits on or possibly measuring the local curvature of distant high curvature regions like near the surface of a neutron star or deep inside a globular cluster, that's an invaluable tool.
So we're establishing the rules of engagement for the universe's most extreme locations. If we can see an atomic transition line coming from a region like that and measure its shape distortion, we are directly measuring the local space-time geometry. The atom becomes a geometric sensor.
Exactly. It connects general relativity, which describes the macro, to the Dirac equation, which describes the micro, and it provides a unified prediction for how matter behaves under extreme geometric stress.
All right, so to actually perform this calculation, to merge the geometric rigor of GR with the complexity of relativistic quantum mechanics, Parker had to lay some groundwork. He had to make some very specific assumptions.
You did. You always have to build a workable model.
So what were the necessary starting conditions to make sure the calculation was manageable but still physically relevant?
There were four foundational pillars, really.
Yeah.
The first is the structural assumption that a metric description of space-time is valid. We're operating entirely within the framework of general relativity to define gravity.
Okay, makes sense.
Second, the quantum mechanical constraint.
Hmm.
The electron system has to be governed by the generally covariant Dirac equation. This is non-negotiable. Using the Dirac equation inherently incorporates special relativity, so you're correctly treating the electron's momentum, energy, and spin. Without that, you just lose the subtle, fine structure and spin-orbit coupling that are essential to see these differential shifts.
So no approximations using the non-relativistic Schrödinger equation. We need the full relativistic description from the very beginning, because these subtle curvature effects are on the same order as, or even smaller than, other relativistic quantum corrections.
Precisely. The third assumption deals with the atom's motion. The atom is assumed to be in free fall along a geodesic of the space-time during the time it takes for an atomic transition.
So it's just following the curve of space-time, no other forces pushing it around.
Right. No rockets, no non-gravitational forces.
This is crucial because it lets us define the atom's rest frame as a locally inertial frame, which dramatically simplifies the metric we have to work with in the atom's immediate vicinity.
And the final condition. You said there were four. The fourth one is a bit technical but vital for defining stable energy levels. The time rate of change of the Riemann tensor has to be sufficiently small on an atomic timescale.
Meaning the curvature isn't changing wildly while the electron is trying to make a transition.
Exactly. Atomic transitions are incredibly fast, on the order of 10-16 seconds. If the curvature were changing rapidly over that time, the energy levels wouldn't have time to settle into distinct, well-defined values. By assuming a slow enough change, we guarantee that stationary states can actually exist and be measured.
Okay, here's where it gets really interesting for the methodology. The choice of coordinates. Parker chose to work entirely in Fermi normal coordinates. This is a very specific choice in GR. Why Fermi normal coordinates as opposed to, say, the more familiar Riemann normal coordinates? That choice seems key to the physical interpretation.
It's arguably the most crucial technical decision in the whole paper. When you calculate the energy levels of an atom, you're fundamentally looking for measurements that would be made by an observer or a detector at rest relative to that atom.
You need a frame that's locally inertial.
Exactly. You need a frame where gravity seems to vanish in the immediate vicinity, and that tracks the atom over time. Now, Riemann normal coordinates, they fulfill that local inertial requirement, but only at one single point in space-time.
So they're like taking a single snapshot, guaranteeing flatness only at the camera's lens point.
That's a great way to put it. As soon as you move away from that point, or as time progresses, R and C start to deviate from an inertial frame pretty quickly. Fermi normal coordinates, on the other hand, are designed specifically for tracking an object moving through time along a trajectory. In this case, our atom's geodesic, $.
So they're normal along the path.
Yes, normal along the time like geodesic. The time coordinate, $6, corresponds exactly to the proper time along the atom's path. And the space-like coordinates are generated by space-like geodesics that are normal to that path. In effect, F and C's give the atom its own local, non-rotating, continuously maintained inertial frame.
So the atom genuinely sees its surroundings as flat in its immediate vicinity. And the geometry, the curvature, appears as a necessary, persistent perturbation on that flat background.
And that perturbation is derived directly from the Riemann tensor components evaluated along the atom's path. It is the perfect setup for perturbation theory.
And the complexity doesn't stop at the metric itself. The paper shows that even the electromagnetic field, the Coulomb force binding the electron to the nucleus, is fundamentally altered by the curvature.
Yes, and this is another profound, subtle point. In flat space, the electromagnetic vector potential AMU from the nucleus is simple. But when the space is curved, Parker found that AMU also have to be modified to first order in the curvature.
What does that mean physically?
It means the geometric warping of space-time affects all the fundamental forces on the electron, not just its motion from gravity. The straight field lines of the Coulomb force, the paths the virtual photons would take, are themselves geometrically distorted by the surrounding space-time curvature.
That's a stunning realization. The geometry isn't just pulling on the atom with tidal forces, it's changing the electromagnetic structure that holds the atom together. The electric field lines are subtly bent.
Exactly. You are modifying the very potential where the electron sits in. And this leads us to the final critical subtlety of the framework, the Hamiltonian. That the whole calculation rests on the Hamiltonian form of the Dirac equation. I bar partialed chi HES.
And to get real, measurable energy values, the Hamiltonian has to be Hermitian.
It must be. In standard quantum mechanics, that's what guarantees your observables are real numbers. But what happens in curved space?
The rules change, I'm guessing.
The definition of the inner product changes, the way we calculate probabilities. In flat space, the scalar product is just an integral of pi dagger psi over space. In the curved FNC system, Parker establishes that pi daggers is Hermitians only with respect to the curved space-time scalar product. This is given by an integral of pi dagger psi.
There's that score term, the square root of the negative determinant of the metric tensor.
That's the geometric weight factor. It corrects for the fact that the volume element itself is warped by the geometry. Without including it, conservation of probability and charge would break down. So, interpreting dollars as the energy observable relies entirely on this curved scalar product, ensuring hermeticity and therefore real energy eigenvalues. It's a necessary mathematical check to keep quantum mechanics sane in a geometric framework.
Okay, so with the full relativistic curved space Dirac Hamiltonian established, the next step is to apply perturbation theory to find those energy shifts. And as is standard practice, you break the full Hamiltonian down.
That's right. R$s is split into T$ plus H101. T$ is the unperturbed part, the flat space-time relativistic Hamiltonian. That's the standard solution for the one electron atom from the Dirac equation.
And H1 is the new stuff.
H1 is the new stuff. It contains all the curvature interaction terms, every single term that is of the first order in the Riemann tensor components. It's the geometric stress on the system.
And this is where it gets tricky, right? There's a challenge here that goes beyond standard textbook quantum mechanics.
There is a very significant technical challenge. Standard perturbation theory relies on using the known flat space solutions, the eigenvectors of H$, to calculate the effects of the perturbation H$1.
Okay.
And that calculation normally assumes that both $90 and the perturbation H$1 are individually Hermitian with respect to the flat space scalar product.
But they're not.
They're not. Parker notes explicitly that neither H$ nor H$ alone is Hermitian with respect to either the flat or the curved scalar product when you separate them. They only work together to form the Hermitian total dollars in the curved space.
That feels like a fundamental breakdown. How can you even calculate the energy shifts that if the components you're using in your matrix elements aren't Hermitian in the basis you're using?
It requires a much more careful development of the perturbation theory. The energy level shifts, the Gay values, they're found using a matrix determinant equation. But crucially, for computational simplicity, those matrix elements have to be calculated using the known flat spacetime eigenvectors and the flat scalar product.
So you use the computationally simple but technically flawed flat space tools to calculate the corrections. How is the final result justified?
It's an elegant mathematical proof that links it all together. The reality of the final energy shifts is assured only by the fact that the total Hamiltonian dollars is Hermitian with respect to the curved scalar product. The math shows that the errors introduced by using the flat scalar product cancel out against the non-Hermitian nature of the split components.
So it all works out in the end.
It guarantees that the calculated shifts are indeed real, measurable eigenvalues of the system. It's a fantastic insight into the rigor required at this intersection of physics. It shows that uniting these two theories isn't just about writing down one equation, it's about making sure the fundamental principles of measurement are maintained through every single step.
Okay, so once that methodology was validated, the next job was to figure out which of the many terms inside that perturbation Hamiltonian 1H$1 was the most important. Which geometric force dominates?
Right. And the analysis involved scaling all the parameters, momentum, radius, curvature. And when you do that, the largest term, one that's going to dominate the lowest order energy shift, is unambiguously identified as frac 1-2 under 7-6 rho for 3.
That's a mouthful. Let's break that down. Rocker bar components of the Riemann tensor, 6 $$ are position operators squared.
Let's focus on the physical significance because this is the most direct link to classical physics. The term rho is fundamentally the definition of the tidal force component of gravity. It relates the relative acceleration between two nearby points.
Okay.
And the 6-molar dependence means the force exerted on the electron depends on the square of its distance from the nucleus, which is exactly what you expect for a tidal interaction stretching across an extended object.
So the largest quantum mechanical perturbation on the electron's energy levels is the quantized relativistic expression of the classic tidal force. It's geodesic deviation.
Exactly. If you take the non-relativistic limit of this complicated quantum perturbation, Parker shows it reduces precisely to the classical Hamiltonian interaction for geodesic deviation. It's the perfect sanity check.
And what about that last part, the thorough three lies? That's one of the Dirac matrices.
Right. It essentially acts as a selection operator. It distinguishes between the large positive energy components, which are the electron states we care about, and the small negative energy components, like positron contributions. It just ensures that this physical tidal interaction is correctly applied to the electron's positive energy states, so we can focus purely on the orbital changes induced by the geometry.
So let's move from the general theory to the specific calculated results for the lowest energy states. Let's start with the most stable state, the 1s12 levels. These are the ground states, two-fold degenerate in flat space.
For the 1s12 level, Parker found a clear energy shift. But the key detail here is that the two degenerate levels are shifted by the exact same amount.
So the degeneracy isn't removed by the curvature, at least not in this first-order calculation. Why is that?
It comes down to symmetry. The shift has to be invariant under any rotation of the spatial axes of the atom's local frame. And our Watt-Layer states are spherically symmetric. The electron cloud has no preferred direction in space.
So the perturbation must also be spherically symmetric to avoid splitting the spin degeneracy.
Exactly. Mathematically, this dictates that the final shift can only depend on scalars or components of the Riemann tensor that are themselves rotationally invariant when you average them over the Laidlaw wave function.
And those are the Ricci scalar, $3, and the time component of the Ricci tensor.
That's right. The spatial components of the Riemann tensor, the ones that encode directional tidal stretching, they average out to 0 when you integrate over the spherical symmetry of the $1 state.
So the $1 state only responds to the simplest non-directional aspect of the curvature, which is mostly related to the presence of energy or mass density.
That's the lowest order result, yes. And it's a very robust result. Parker's shift calculation is valid to all orders in alpha z, the fine structure constant times the nuclear charge. So all the subtle relativistic corrections are baked in.
Did he suggest what might happen at higher orders?
He did. He stated his intention to carry the calculation to the second order in the curvature. And that second order calculation is where you'd expect the finer details of the geometry to emerge. It should result in a tiny splitting of the 1s12, removing the degeneracy and revealing even more geometric information.
Okay, now let's move up to the N2 states, the 2s12 and 2p12 levels. These are the states famously studied in the context of the Lamb shift, and they're fourfold degenerate in flat space. This is where the differential effect must become clearest.
It absolutely is. You have this fourfold degenerate state space. And when you apply the perturbation each $1, you have to look at the matrix elements between these states. This is where selection rules based on parity come into play.
Okay, remind us simply, what is parity and how does it separate the S and P states?
Parity is the behavior of the wave function if you flip all the spatial coordinates. The Sevicities, like $1 and $2, have even parity. The wave function stays the same. The states, like 2p-arsers, have odd parity, the wave function flip sign.
Right.
Parker uses this rule to show that the largest curvature perturbation term we identified, that geodesic deviation term proportional to Fruitfulness and 7 Morais, it actually vanishes when you calculate the matrix element between a 2s12 state and a 2p12 state.
And why does it vanish?
Because perturbation theory says an interaction operator can only mix two states if the operator has the right symmetry properties. The tidal force operator, $6 to $7, involves squaring position coordinates. That makes it an even parity operator. An even operator cannot cause transitions between or mix states of opposite parity.
So since 2 stellars is even and 2 polars is odd, the matrix element between them has to be 0.
It must be 0. It's physics being dictated by geometry and symmetry. The dominant geometric stress literally cannot mix the S and P states because of their inherent quantum mechanical spatial organization.
They separate cleanly.
They separate cleanly, which means we can calculate the shift for the 2p auto and 2pr groups independently. And the final calculated shifts, in the lowest order, show a dependence only on that Friedel component of the Ricci tensor, just like the $1 seat tape.
And what are the results?
The shift for the 2s12 states is E1 2s12, and the shift for the 2p12 states is E-6 2p12 tonus 1 tonus 12. That is exceptionally clear. Both levels are pushed up, but the 2a state is shifted by 7/6 units, while the 2p state is shifted by 5/6 units. The difference is 2/6 or 1/3.
Right. That differential shift of 1/3 on 1r is the curvature signature for the N and 2 levels.
That is the observable core of the result.
It is. And Parker connects this back to observability, noting that this 2s-2ps splitting caused by curvature will be of the same order as the Lamb shift when that characteristic radius of curvature is about 199 centimeters.
Which we established is a massive curvature far beyond our solar system. It is. But he also considers the theoretical implications in the non-relativistic case. He notes that if dollars were significantly smaller, say less than 10 centimeters for hydrogen, the curvature perturbation would actually be larger than the typical relativistic fine structure correction.
Hold on. You're saying that in an extremely warped environment, the geometry of space-time could have a larger effect on the atom's structure than special relativity does.
Precisely. In such an environment, the geometric influence would be readily observable. It would dominate the subtle relativistic quantum corrections that normally define the fine structure of the spectrum. It reinforces the idea that in extreme gravitational fields, geometry can dictate fundamental atomic structure.
This brings us full circle to that connection with classical gravity. The fact that the lowest order terms found in these shifts are exactly the same as what you'd get using the classic non-relativistic Schrödinger equation plus the geodesic deviation interaction. That's a huge testament to the consistency of physics.
It's the necessary bridge. It confirms that the quantum corrections respect the classical limit. But let me flip your earlier challenge back on you. If the non-relativistic approximation works so well here, what truly unique benefit does Parker's full Dirac treatment provide?
That's fair. If the classic Schrödinger approach with a tidal term gives the same answer for these N2 shifts, why bother with the incredibly complex Dirac equation?
The Dirac calculation provides validity across the entire spectrum of interactions. First, it correctly accounts for spin and fine structure, which are completely missing from the Schrödinger picture, and those would become critical in higher order calculations or with heavier nuclei.
Okay.
And second, and this is more subtle, the relativistic framework provides validity even when the curvature term is too small to be retained in the non-relativistic limit.
What do you mean?
In weak fields, like near Earth, the curvature effect is minuscule. When you use the Schrödinger approximation, you're already ignoring relativistic corrections proportional to alpha squared. If the curvature perturbation is even smaller than that, the classic model might just drop it as irrelevant noise.
But the Dirac framework keeps it.
The Dirac framework maintains the integrity of the physics down to the smallest possible scale. It correctly integrates the geometry with the quantum field theory, even when the effect is far too small to see. It's a guarantee of theoretical consistency.
So it's not just about getting the right number, it's about guaranteeing the theoretical structure holds up, ensuring we haven't missed a fundamental interaction because of an approximation.
Precisely. Now let's address the practical reality of measurement. We need to distinguish between what the atom feels and what a distant astronomer sees.
Right.
The energy shifts, I-dollar that Parker calculated, those are what would be measured by a detector located near the atom and at rest relative to the atom. They're defined strictly in the atom's locally inertial proper frame.
But a distant observer, looking across vast cosmic distances, would see a lot more noise on top of that.
A lot more. A distant observer would see these Z shifts, but they would be superimposed on Doppler shifts, uniform gravitational shifts, and cosmological shifts from the expansion of the universe.
But those other classical shifts affect all the spectral lines uniformly, don't they?
They do. They shift the entire spectrum like a transposition, and that means they are mathematically separable from the unique differential curvature effects calculated by Parker.
And that separability is the key to observability. If the curvature effect wasn't differential, we could never isolate it from the background noise of standard gravitational redshift.
That's the entire point. The geometric signature survives the transit across the cosmos because it changes the shape of the spectrum, not just its overall position.
Now, you mentioned a subtlety about where these results apply. The shifts for the S and P states vanish in a region where the worker component is zero.
Right, and trigger is often interpreted as being closely related to the mass energy density in the spacetime.
So, in a perfect vacuum, far from any matter, where $3 zero, does the effect disappear for these specific levels?
To this specific first order, and for these highly symmetric S&P states, yes, the dominant effect related to mass density vanishes. However, Parker is very clear that this is not true for other energy levels or for higher orders in the curvature.
Ah,
For instance, he provides the non-relativistic shifts for the three two-polydopti levels. And these shifts are dependent on the spatial components of the Riemann tensor, specifically Becker-NMA.
the components describing purely geometric warping, even if no matter is present.
Exactly. So even if you're in the empty space surrounding a black hole, a vacuum where R is zero outside the event horizon, the geometry is still highly warped. And those spatial components of curvature could still induce a differential splitting in other, less symmetric atomic states.
This is perfectly illustrated when Parker brings in the Schwarzschild metric, which describes the space-time around a black hole or star.
It is. If you imagine your local coordinates are aligned, so the x-axis is radial pointing toward the black hole, you find specific components of the Riemann tensor are non-zero. The components that encode radial stretching, like ρ dollars, are large and relate directly to the mass and radius.
And the other directions?
The components related to tangential squeezing, like Lieways, are also non-zero but have a different magnitude or even sign. This difference, the non-uniformity of the curvature components, is the tidal stress. If we calculated the shift for a state that was sensitive to direction, the specific values of these components would tell us precisely how much the atom is being radially stretched versus tangentially squeezed.
It makes the geometry tangible. It gives you input values showing exactly how a black hole's geometric distortion affects the atom's internal energy levels.
And finally, Parker compiles all of this into one powerful statement using a covariant formulation. It uses the atom's four velocity and local unit vectors.
And what does that final comprehensive expression tell us about the atom's fundamental properties?
It summarizes the total energy momentum of the atom. And the fundamental implication is this. The total rest energy of the atom is not just its flat space energy. It's fundamentally affected by its motion and its position relative to the surrounding curved spacetime.
In short, the geometric environment dynamically modulates the atom's mass-energy equivalence. Its fundamental properties aren't fixed constants.
They're subject to the local warp and weft of the cosmos.
This has been a tremendously dense and illuminating deep dive into the 1980 work of Leonard Parker. We started by asking if the light from an atom could tell us about local gravity. And the answer, thanks to a careful application of the fully relativistic Dirac equation, is a definitive yes.
It is.
By moving from the classical approximation of geodesic deviation to the full quantum mechanical treatment, this research established the unique differential signature of space-time curvature on the energy levels of the simplest atom.
And the power of the results really lies in their universality. The expressions derived for the energy shifts are independent of how the curvature tensor of the spacetime is generated.
It doesn't matter what's causing the curve.
Not at all. Whether that curvature comes from a primordial density fluctuation, a massive star, or even some exotic matter, the effect on the atom's internal structure is governed strictly by the derived tensor components. It separates the measured phenomenon from the source, making the atom a pure geometric tool.
It's a fundamental link between the geometric description of gravity and the probabilistic world of quantum mechanics, showing that the two fields must eventually speak the same language. So for you, the listener, let's end with a reflection on that challenging scale. The 199 centimeter curvature radius. We established that the effect is ridiculously tiny in weak gravity, far smaller than other quantum corrections like the Lamb shift. But consider what happens in the absolute extreme environments, the interior of a massive neutron star, or the space just outside a supermassive black hole's event horizon.
In those locations, the radius of curvature dollars is often measured not in thousands of kilometers, but potentially in tens or hundreds of meters. If dollars is significantly smaller than 199 centimeters, the curvature perturbation might not just be appreciable, it might dominate the physics.
And that's the provocative thought we want to leave you with. In those extreme cosmic environments, the local geometry itself might fundamentally rewrite the rules of atomic and particle physics. The composition and behavior of elements, their chemistry, their spectral fingerprints, everything might be dictated not just by density and temperature, but by the relentless geometric warping of space-time itself. It turns out, To understand the physics of a black hole, you might first need to understand the warped tidal stressed orbit of a single electron.